In addition to all of us gathered here are two other personalities that I would want to acknowledge. And I have with me Dr. Charles K. Nye, who is the president of the American Concrete Institute, spanning the years 2022 to 2023. So you are welcome to join us. Thank you. Then again, we also have Dr. Emmanuel Atiobe, who is the CEO of SEM Innovations. They are basically civil engineering materials. And so as we dialogue further, let's tap into their expertise and learn more from them. At this point in time, we would want to observe a presentation on the introduction and application of fiberglass reinforced polymer bar. That's a mouthful, but I'm sure the resource person will help us break all these down. Then we can learn from that. And so to do that, I'll kindly call on Victor Golu, who is the director of Viva fiberglass reinforcements, to take us through the presentation, after which there will be a session for questions and answers to understand what exactly fiberglass reinforced polymer bar does and how this can be helpful to us in our engineering fields. Thank you.
Good morning. I'm very glad to be here. Once again, my name is Victor. I would say that in the beginning of our event, some nice words were said that we're supposed to make some money. So I hope that after my presentation, this material will help you and will help your clients to save some money and, of course, accrue some money as well. So I will start with a brief introduction of our company, who we are, where we are, what we are doing, just like some couple of words before we will come to the material itself. What is it? Because we recognize that although some of the engineers are already using it, some of them are still looking into it and still trying to discover this material in their application. So Viva fiberglass reinforcement came to Ghana in 2017. This is the year when all the design codes for the fiberglass application was like these design codes were adopted in Ghana by Ghana Authority. And basically, since that time, the practical implementation started. We started marketing our product. We started introducing our product to the engineers. We make some couple of first introductory seminars together with the institution, and I also was doing some rounds all throughout the country with some universities, and also introducing this product to engineers to let them be aware about the material, which might be an alternative in concrete reinforcement. So for this 5 years, so far there are a lot of projects being done. I will show some of the examples of it, and we'll try to give some additional information about the material. So let's talk on the material. Let's not talk about us. At first, I will say you can see there are some slides on that screen. Unfortunately, not yet. We are having that screen open. So if you can. So you might be trying to look into that screen too, but of course I will comment on it. So I will start briefly on a historical context of the product to let you know from where it comes from. At first, like the first tries to produce this product, was in 1940s, and basically this was a military technology, because by that time the raw materials for this material was quite expensive, and it was not affordable to use in a regular civil construction. That is why, because of its non-magnetical effect and because of its non-corrosion and some other properties, it was used mainly for the military, for the air bases where the radars will not be able to see the structures which are standing, and also it was used later on. It was used in hospitals because, again, it's not magnetical effect of MRI rooms. It's like this product does not create any effects to the equipment working in that area. So mainly the technological boom and the bigger usage of the material starts from 90s. This is where in USA, Europe, Japan, in China, more of the usage of the material starts coming, and currently we have a lot of different examples of application. I will show you, for example, we are having some of the this. I don't know whether you will be able to see. In 1957, there is a house of future. It's in California, in Disneyland. It was the first house. It was like a trial built with fiberglass to see how it works. They were trying to break it, I think, afterwards in some 15 or 20 years. And actually, it was very hard to break it because they thought it's probably like the properties of the material will be downgrading, but no. Still, the structure was there, but I think because of some other issues, they decided to demolish it. Nevertheless, it was like one of the first structures that's open to the people where it was used. We have also some other samples, mainly in the road construction. You can see some highways in Canada. We have railway tunnel, for example, under the River Thames in London. It was 2012 when it was built. We have Japan, some hospitals. So, like, just to give you the brief explanation that this material is not something new, not something that was not, I mean, like, here and then just it's here, so like can we use it? It was some time already when people were using it, when there is application, and we are the first one who came with this technology to Western Africa to use this technology and other Western. So you can see some other bridges, some other road constructions where the fiberglass was used. Just the brief one. So I think all of you have a sample of the material. I will try to explain what is it because there are actually we'll have the Q&A session, I think, afterwards, after the presentation. So I think if you have some answers, I will try to reply to all of them afterwards. So you can just note them, and afterwards I will reply. So
yeah, sure. We are going to send this.
Yeah, it's possible. You can leave your if you I mean afterwards you can share this with your emails. Afterwards, all the information, the presentation, or some other licenses, whatever, like the documents might be sent. I'll be sending share with all of you.
Thank you.
So with regards to the material, the material you see in your hands is the GFRP, glass fiber reinforced polymer bar. It is one of the 4 types currently existing of FRP, of reinforced polymer bars, which might be found all around the world. The other types is the basalt, carbon, and aramid. So what differs is that the main one of the composite of this material is the glass. That's why it's called GFRP. So if we are changing the base for to make this rebar, we will use rather basalt, carbon, or aramid. The most expensive ones are aramid fiber reinforced polymer bar because of their parameter. The tensile strength there is extremely high, but they are the ones who are still mainly used for some special constructions and not like that's widely used around the world. Main type which people are using are the GFRP and GFRP, BFRP, a bit less of the carbon. Why we choose to introduce the GFRP first? Why we are producing the GFRP? At our concern, it is because the balance between the tensile strength and the other parameters is the most balanced, the most average in GFRP. So, like as an introductory product, as a product which can penetrate the system, we have choose the GFRP to start the production. The advantages of the GFRP compared to the other types of the fiber polymer is that it is transparent, like I just said earlier, transparent to magnetic fields and radio frequencies. And additional is that it is thermally and electrically non-conductive. So meaning that if, for example, you will start heating it on one end, the other end will still will be cold, will not get thermally damaged by the other side. And the electrical is basically also. Well, apart from it, it is also stable to the aggressive environments, like the acidic environment. It might be used in some special constructions if you come to the chemical plants, because this material resistant the chemical environments is also like quite good to use it in that. So these are four main types of the bars, which might be used, and like as I was saying, we are using the GFR. Next slide, please. Briefly about how do we do it. This is a graphic, a kind of a picture graphic of how you can see the production line. The two main components of the GFRP is the glass rolling, is basically the glass filaments, a lot of glass filaments inside of the bar, and then the mixture of the resins. So when it starts with the glass filaments, then they're coming through the resin bar, and we are forming the ribs on a bar, so it becomes the rebar, like you can see, like the regular steel rebar that is available on the market. And afterwards, it comes to the ovens, where as soon as it is heated, it becomes solid, and it is ready to get used. And afterwards, you cannot like actually blend it. You can do other things with it because the blends become so the standards, the design codes is saying that you are rather using the producer, the manufacturer, can use the ribs for this material, or can use the sand in order to receive the bonds, like get the bond properties like when it's concrete. We ourselves, we decided to basically it's not against the design code. We are using both. We are having the ribs and we are having the sand all around the bar too, in order to use the bonding properties in the concrete. By the research we've done so far, it shows that the sand-coated FRP bars are showing the bond, like the strengths when we are trying to take it out of the concrete of 10 to 12 MPa. So these properties are quite good, and I mean that's why we are using both in our production. So briefly, that's how it looks. The process called pultrusion. This is the process of polymerization. That's why it's called a polymer bar, because it's the process of polymerization. The different types of the resins, like the composition of the resins we are using is our own more or less secret. There are a lot of different types of resins used, and actually receiving the different parameters of the bar itself. So the process itself is very easy. It's been known also for some time, but the composition of the chemicals and the parameters you are receiving in your bars, that's what prepares the bar to bind to this slide. So after we got to know some of information about the material, like what it consists of, the main issue is where you can apply it, whether there are some areas where you can apply and where you cannot. I would say that mainly this material might be applied in all types of construction, all types of application, in consideration with the other parameters, of course, but mainly so far I cannot say that some of the areas you cannot. Some of the areas, for example, like I was saying, the chemical engineering, like the chemical, all the marine applications might be done with it. It will not affect the rebar itself. It will save the lifetime of the structure. Apart from it, it's also good for some like the regular concrete, like the regular civil construction work that we are having, like residential, industrial roads, bridge decks, all the type of the other application where which are existing there. This product might be used there. This next slide. I'm very glad, like now we are coming to the standards, the design codes. Like was said, we have the head of the American Business Institution here, which I'm very glad to hear that. When we, and I'll explain why. When we came to Ghana, when we on a stage of design of our factory and of thinking how we will trade the market, we started thinking about the design codes and the standards on which like the engineers will work with, like how to work with this product, how you will know that like it's good, bad, what are the parameters and elements. And we had a couple of meetings in addition, like with the Ghana Standards Authority, and also we've been analyzing the different design codes. The Euro code, we've been analyzing the Canadian, the ACI codes, ISO, like the different type of codes, which and in order to choose which one we are going to mainly look into. And GSA was advising us, like it was like the joint decision that we should use the ACI standards and adopt the ACI standard in Ghana. At the moment, as I was saying in the very beginning, from 2017, we are having the GS standard. It was identically adopted from the ACI standards for the usage of the fiberglass. So these design codes that are seen there, they are the ACI design codes about the arch. It's for the bridge decks, but the first ones, about the last one, they all are ACI ones. And at the moment, as I was saying, they're GS standards. Is it possible? Sometimes engineers want, they're asking whether it's possible to use the other design code, or how, for example, if you are using some of the projects, people are designing with the Euro codes or with the British standards, and why do we choose the ACI actually? The answer to that is very simple, because among the other design codes, among the other standards, the ACI particularly, the ACI 440.1 R15 is for the structural design. Like it's actually very, very difficult. It's very detailed code. So for the engineer, for the person who sees the product first, it's very easy when the person is going through the design code, it's very easy to understand the parameters, the forces which are acting, the advantages and the peculiarities of the product, where to use, when not to use. It is very detailed. If we are coming, for example, to Euro code on the fiberglass enforcement is actually pretty short. We just say that you can use it. So you just should use the parameters. The parameters the manufacturers is saying. For example, you are taking the tensile strengths, the shear strengths, the other parameters that manufacturer is saying that has for this material, and then you are just applying. So as soon as you are having the maybe GSA or the Bureau Veritas certificate for the particular batch of the production, I mean, you are just applying. The ACI is a bit different, and that's why we need to use the ACI. Because again, it is very detailed. Afterwards, if some of you want, we have the GS standards. We can share with the engineers, with the structural engineers who are interested in it, so they will be able to go through and read more. Because actually, 1 hour is just like the introductory starting presentation and the practical applications. So we don't have that much of the time, but as of the particular, the structural aspects, how to design, where to use, where not to use, you all will be able to find that design code. Please, next ones. So we are coming to the major part of our presentation of the advantages of GFRP, of the practical implementation, how to use, where to use, what are the parameters of it, and why the material that I'm showing to you, why it deserves to look into it. First of all, the main advantage, we will start from the tensile strength. This is the main advantage of this material. The tensile strengths of our material, the latest tests are showing the test from 1,000 to 1,200 MPa. This is what's been tested. That's what's been confirmed by GSA, by some other laboratories. We also have the Bureau Veritas. We're doing tests like as the short independent parts of the test. So the tensile strength is much higher than on the steel ones, and this is the huge advantage. Because of it, the other benefits will show up. I will explain later on, but this is one of the huge advantages. As of the other parameters of the material, when it comes to the standards parameters of it, we come to the tensile where we explained it to you. Then, if we are coming to the, for example, when we come to compression, the compression parameters of this material are mainly from 60 to 50% of its tensile strength. So it's more or less, when we're talking about, it's around 500 MPa approximately. So it's more or less the same with the steel. That's why the other consequences of it I will explain when we come to practical application structures. So the compression is around 500 MPa. When it comes to the shear strength of this material, the minimum guaranteed tensile shear strength is 125 MPa, which is lower than steel. Steel, I think it's around 250 or something. But the latest improvements in the technology, currently we've been able to reach the shear strength of 200. That's what we are having. The technology is actually all the time developing. We are all the time changing the types of the raw material we are trying to improve it. So the shear strength is still lower from the steel, but we are moving to the parameters to get the same level of the shear strength as the steel has. Next parameter is the modulus of elasticity. The modulus of elasticity is 4 times at the moment, like best standard, is 4 times lower than steel. So if steel one has 200, ours, this is the minimum where the standards, like how the design policy is supposed to be. When you are designing, that's what the drawings. Although at the moment, because of the change, probably it will lead afterwards to review of the design code. We have not yet reached that, but we are looking about it. Currently, the modulus of elasticity mainly works with the core products of the material, mainly the glass. So the way that that parameter is of the glass, the same more or less parameter that rebar will have afterwards. So the technologies of the raw material are now also advancing, and at the moment we are using the glass filaments that are having the modulus of elasticity of around 80-85 GPa at the moment. So looking on this properties of the material, the question is where can we apply this material? Where like in which members this material will apply? And the best application for this material, I would say, is for the horizontal members, where the tensile strength plays the key role. So for your slabs, some partially like for your beams, you might be using it in your application. When it comes, the question comes to the columns, whether it's possible or not to use columns. Like I was saying, the design code is saying it is possible to do so. It also has some other remarks with regards to the heightness of the structure. It says that if it's more than 4-story building, you have to do additional parameters also stated in the design code. So like it's not that And we ourselves, from all our practical experience that we see, mainly engineers are using it in columns for the structures at the seaside, mainly like maybe some hotels. It's just like a story, or maybe like one-story structures, not the big structures, but where the corrosion mainly destroys the structures. Because as soon as you're placing the steel lanes on half year, 1 year, I mean, your structure is basically like you already have to do some preparation or other effects. So, but with this material, since it's not corrosive, it's a good alternative to it. It comes to some cost effect. I'll come to it, but mainly it's possible. So when we are coming to the direct structural issues, whether you can do it in a column or not, yes, you can do it, but the factors and the parameters has to be considered. That you have to look for the shear strength, pressure strength, which is lower, and I mean it's different. Then the behavior when it comes to the modulus of elasticity and when it comes to slabs, how it works, because it is lower, definitely that's when it comes to the steel, we have the yield strength, and then we have the ultimate tensile strength when steel will break. So for some time, it will the steel will elongate, and it will give some additional strength to your slab, to your structure, until it will collapse, until it will break. So the question is, and the engineers were asking me, like, if so, if it's that low and like basically the elongation is around a couple of percent, can we use it in the slabs? Because if not, it just will, I mean, like, it will collapse, and that's all. I mean, like, just like that, like, you might be sitting there and then it will collapse. The situation with it is a bit different. First of all, when you are using the design codes, there are there, and when we are giving the technical specification as a manufacturers, when we are listening to you, to our engineers, we are using the minimal, the tensile strengths, which is the guaranteed by us as a producer, and the one which is mentioned in the design code. This is around 760 MPa, around that one. So we still have that additional strength. If we are saying now we're around 1,100 averagely, we still have that additional, not double, but almost both double of the extra tensile strengths. And apart from it, even for example on a slab, whereby it's like 2% from 10 centimeters, for example, it's like 2 centimeters. So even from the small cracks, you already will be seeing that something wrong with it. So it's not like it's going to break just like that, and I mean you will not see any effect. Then your structure collapses. No, not like that. So that is why, together with the other factors, again, that I was saying, which you might be going through the design code and look additional details, I won't be able to be all details at the moment. It is possible, and it is applicable, and it is used widely for the horizontal members where the tensile strength is mainly pure. Then it is the other question and the other examples of application where at the moment any engineers are practicing in, for example, the usage of retaining walls. As well as we are having, for example, I will show afterwards some pictures of it. For example, some of the retaining walls that were designed, and at first it was used like the vertical bars we used with the steel, and but the horizontal ones were used with the fiberglass. We start with this one, like with some couple of trials, we see how it worked. Then with the time we moved, like it was redesigned, and it was fully designed with the fiberglass. So it is possible, again, as I was saying, everything depending on you. I do like to work with engineers, because mainly you engineers, you are open-minded, who like to experiment, like to work on a different tasks from the different corners, and like answer to that. If in general, when we are coming to the parameters, I wouldn't say that like this material, like sometimes people are saying that, okay, the parameters are lower compared to the steel. then it is bad. I wouldn't say it is bad or good. It's just of the, like, when we are talking about figures of the property, it's about the figures of the property. Steel also has its parameters. For example, the tensile strength, I don't know, 450 MPa, for example. Is it good or bad? It's not good, it's not bad, it's just 450. So when you are designing, you're just considering that this is the fact, it's a matter of fact. This is the figure of it. The same thing comes with the fiberglass. It doesn't have good or bad parameters, it just has the way it is. So when you are designing, you just have to consider them and look and answer to that tasks, that engineering tasks that you are facing as an engineer, as a structural engineer, and like replying based on that. Now, when we are coming to a bit more about the practical implementation. If you remember, when I was saying about the production, I was saying that as soon as we are heating it, it becomes solid, and you will not be able to bend it. The issue comes with this material. The issue comes with the bends. This material cannot be bent on site to 90-degree level. So you can see, I will show that to all of you. We have some oil here. That's how material comes. So like you can do an arc, you can cover it, of course. It's not that you cannot bend it at all. It's just that you cannot do the L shape, for example, or the U shape in the design and use it. This turns, this L1, U1, or whatever it is, they might be prefabricated. They might be done prefabricated at the factory upon the orders, but at the moment we are not producing them, and I mean we are more into the trade back because it's just like it's faster for the clients, the engineers to get into technology. That's why we decided to bring the banks in order to fully avoid the steal. So with the fiberglass, you cannot bend it. Not the question is how are you using it? How do you use it? For example, like I just said, you're using it in the beams. So like you need to do the turns, or for example, in your slab, you have to connect the slab to the beam because like if the slab is connected, you also have to do the bends. The answer to that is that this material is like works good together with the steel. So you are mixing this material together with the steel, and where there is a need to do the bends, you are using the bends with the steel, doing the regular overlap with the regular 40 sizes of the diameter rule, and you will get your body. You have your curves. You will have the stirrups. Like as of the stirrups, again, the main parts you are using the straight. For the straight ones, you are using the fiberglass, and for the stirrups, you are just using the regular steel, which you can bend and which you can use. Then again, like with the properties of the stirrups, that they give you that strength, that property that's also supposed to be there according to the designs. So this material is not like when I'm introducing it, it's not something that can substitute steel for 100%. And we are not saying that this material, like just throw your steel away and use fiberglass. No, we are saying that we are giving you an alternative, something new, something innovative, something with a bit different parameters, but something that you might be substituting the steel. Significant. Why? Because your slabs and your beams, this is around 70%, from 70 to 80% of the reinforcement which is coming for all of your project. The columns, they are not that much of the steel which the main steel which is using for the slabs. So that is why maybe for some 17% you will be able to change the substitute steel with fiberglass. Now the question is, why do you have to do so? If this, like this material, I mean, some of you should ask that. If this material is not the panacea, like you cannot throw out the steel, like cannot get the zero rust, the other things, why do you have to use it? And the parameters are different. It also comes in additional with the tensile strengths and the other things. It comes additional with the savings, the economical sense. This material. The material we are having is comparing to the steel is around the moment, around 40% cheaper comparing to steel. And I guess you will agree that 40% is something significant that might be saved per ton, equivalent per ton, and it might be saved for your clients, for your, I don't know, like personal construction, whatever it is. Like these costs are significant, and that is why the combination of the two will give you, from one side, will give you the strong structure, the structure with the figures that might be, and at the same time will save your clients, will benefit from it, and I'm sure and I hope we will get more of this from it, because I mean they will be satisfied, so the people will start talking that you are using it. So that is the main advantage of this. First of all, because of the tensile strength, you are able to use this material and save it. How are you doing that? Mainly, you are doing that by reducing the diameter of the bar which you are using in your slabs. For example, now I get the discussion will come afterwards on how to use it. Some of the engineers, what they are doing, for example, if you, let's say standard situation, we are having the 12 mm bar we are using for our slabs. Instead of the 12 mm high tensile steel, you are reducing the diameter approximately to around like 8 mm of ours. But you are doing the same centers as if you are doing, as if you are designing with your regular steel. If it's 150, 150, you are doing the same center distance. It's just that you are reducing the diameter of the bar. So you will see the same tensile strength comparing to the regular steel that you are using. Some of the engineers doing it in a different way. They are a bit reducing the diameter, or maybe using the same, but they are increasing the spaces in order to receive the same strength. So it's like, it actually depends on the approach, it depends on the standard. Some of the engineers, for example, I know they still get used to BS standards, and they are rather increasing the distances a bit, then reducing the diameter. So like it all depends on the engineers. That's I'm just explaining from the practical experience that I'm having in conversation with engineers who are applying it. So that is why you are able to use the lower size of the bar, receiving the same strength, and at the same time saving the cost with this material. The question comes is that whether you can use the size to size. Yes, you can use the size to size. No problem, you can use 12 to 12. The main question is why? Because you will receive extra tensile strength. It will not do any additional job for it. You will basically overuse the product. Because the parameters of it, again, nowhere, I'm talking like, if you are saying like, maybe it was the biggest, nowhere in a I think, design codes, probably I'm wrong, but it doesn't seem like it's to be corrected. Nowhere in design code saying that for this building, use 16 mm and don't use anything else. You are using particular size, again, based on the properties of the material. And it's the same thing with this material. You are looking on the size. I'm not saying, when I said about 12 to 8, I'm not saying that you should use 8 in all of the cases. No. I'm saying that sometimes you might need a bit more of the strength, you're using 10. And I will show you some of the examples where in the slabs, engineer, instead of the 12, was using the 10 mm. It all depends on your design, on the forces which are there. And again, with the assistance of the design codes, you will easily get to it. So this is with regards to the economical benefits, with regards to the properties. Then with regards to the lightness, I mentioned to you that this material, I think you can weight it, it's 5 times lighter than steel. It will bring, of course, it will bring the lightness to the structure. But at the same time, when we are coming to the economical side of the business, how do we do about it? I will explain later on. And then, there are the benefits of it. And apart from it, with regards to the transportation too, that this material might be easily transported even with your private cars, with the pickups, and you're saving actually a lot of money on it because of the lightness of it. Sometimes, I wouldn't say it's about the engineer, but sometimes when you're coming to the site, clients are very, especially when they see it in the first time, when engineers like introducing it and they say, okay, please come to see the clients, I mean, I can use the product, like explain the economical, the mathematics and other things. Then when I'm coming, like some of the steel benders, for example, on the site we had that they were trying to look into it, saying that no, it cannot be that strong. I will show it's light. Sometimes people are thinking that if it's heavy, it's supposed to be strong. Like the heaviness of like how much it weighs. The weight does not work anything with the other forces, with the other strengths. And even in my like experience, I experienced that one steel bender was trying to bite the material. Maybe he was thinking that he would be able to break it because it's that light. That's, I mean, like, you couldn't believe that this material could do something or work somehow. So there are a lot of the perception with this material too, which we are facing. And again, that's why we're glad that we should work with the Society of Engineers, because you are the one who can introduce this product to your client, who will know particularly what are the parameters of the particular, like of the material, where to apply, where not to apply, where there are the risks, how to handle them, and how to work with this material. So I was saying about the other advantages with regards to that zero corrosion, because there is nothing called corrosion. It's cheaper, the tensile strength, and it is light. Now, I will get more into the cost effectiveness, and then I will come to the transportation of the weight. This next slide. The advantages, like I was saying, like in our presentation, when you will see it, we are saying that you can save up to 50%. We are not saying the particular percent that you might be saving. I will explain you why it's up to. And first of all, we are coming to the direct savings. The direct savings, which is calculated here, we are saying that the 8 mm high tensile steel, we can substitute with 6 mm of GFRP 6 mm. If you are doing so, now we'll come back to the weight. We are not working in tonnage when we are coming to the fabric. We are working with lengths. This material 5 times lighter, so we just cannot do with the weight, because if I give you 1 ton of mine, be like too much. You will not. Okay, we just have some additional stock, and we will be reselling it later on. So if somebody wants to buy 1 ton of fiberglass, that will be better. How you are working with it? We are working with the lengths. Each ton of steel has particular meters in it based on the weight. So what we are doing, for example, if you will see up there, that 8 mm steel has 2,531 meters. That one is the standard length for 8 mm. I mean, it doesn't change whether it's the high tensile mile, it's just like the standard length for the 8 mm of the steel. So what we are doing when we are saying that alternatively we are cheaper, like alternatively don't, is that we are giving you the same meters, the same lengths, but of our 6 mm. So when we are calculating the savings per ton, equivalent per ton, that's why I was saying equivalent, is that we are having 1 ton of particular size of steel. You know how many meters in that one, and then we are just giving you the same length, but with our price. So if at the moment it's around 855 USD, is the regular high tensile steel is around 11,000. Our ones will cost around $531. It's just that, I mean, like it's mentioned here, though we all are trading in Ghana cedis, but with the current economical situation, it's a bit difficult, so I will have to change the presentation too fast. So that's why, like, I mean, I just make it in USD for the approximate analysis. So the main savings are the direct savings. Then we are coming to the additional ones. The second biggest saving that might be shown is the savings based on the overlaps. This is the example of how the material looks like. Sizes, this is the 6 mm. The sizes from 6 to 12 mm are coming in coils. So what does it mean is that if, for example, you can imagine this is the slab, you are just unrolling the coil by the size that you need, by the size of your slab, and then just adding the way how you need it. You don't have the overlaps. You don't have this weight because basically the overlaps don't do any job. I mean, they just for you to have the enough, the joints and to do it. So because you are basically, remember I mentioned that at the ends you still will do some, but on the main lenses you are avoiding it. You will be able to set approximately additional around 5% on top. Plus, this material, because it is very light, this is 150 meters, 500 feet. There's still benders if it comes maybe like to the slabs or some first story, second story, wherever it is, to carry the material with themselves, to carry like the workmanship with the material will be faster. So it's the additional savings with the labor costs, with some other applications that you might be saving. This slide. And additional ones is with regards to transportation. Again, because it is lighter, you can transport 5 times more comparing to what you transport with the steel. And the material comes in a coils. You can come with your pickup. There are the coils of different diameter. You can come with your pickup, and like the coils come like coil into the coil, and just take equivalent of maybe 2 tons of steel with the length, or maybe even up to 3 tons with your own pickup, which means that you are not paying any extra cost. You're just paying for your fuel that you are going, which also a huge benefit with regards to the current prices. So these are the main economical points. And again, like I was saying, with regards to transportation of the material and the way how it comes. The sizes from 12 mm and above, they are coming with the 12 meter length, but the standard length for the high tensile steel. But we also we can do the customized sizes based on the project. I will show you later on this. Let's come to the practical. So I will show you. I will comment some of the pictures, and I will show you what I mean about it. So these are some of the examples of the practical implementation of some of the slabs that being done with the material. This is the industrial, industrial area is the GB Foods. They were doing some of the slabs there, the factory. So this is the slab. It changed there, but it didn't change. So yeah, like the additional slab. This is the slab for this water tank on top of this slab. So like this is just some samples of slabs. This is the slab at Atomic Junction Palace Mall, the current palace at Atomic Junction. Some slab there. Just the regular residential project. This. Change that. We change here. Okay, let's look for the meantime. Let's look at this here. You remember I was mentioning to you that I'm not saying to you to use maybe 12 to 8 as I was saying as it is a standard. For example, let's look into this project. This project is I think it's a church of something in Medina. It's like actually a very huge project in the form of building like that. That's what. So the engineer here was using the 10 mm for his slab. I mean, based on his calculation, using the same distances, just he was making it 10 mm for his slab. One. Okay, let's start looking at that. So some other examples. Let's just go ahead. This is the fertilizer factory around also Tema industrial area. It was using the beams. The span of the beam, the total beam is around 48 meters, I suppose, and it's separated on 3 sections. I think it's something like 18 meters and some other ones. So for this particular project, we produce the bars of that length, 18 point something meters. So they also do not have any overlap. It's one big long bar. So for us, we can do whatever sizes we want per the drawings, by the design. Also additional benefits for the client because we will not get any overlaps. Additional applications in the beams. Tamale Stadium project.
Next.
This is the Kumasi Road project. Sorry, Kumasi Road. Okwasi interchange. They use some there too. Just some of the PC. This is the beach resort I was mentioning to you, the hotel where it was used also at columns. The swimming pools were also possible to use. Go ahead. Some of the marine construction MPS, Tema Harbor. Some of the industrial, like the regular. So that's briefly. That's briefly. You can write here our number or the website. So that's briefly about the product. I can see that the time is already passed. So thank you very much. I'm done at the moment. In case there are any questions, I will be grateful. Thank you very much.
Thank you very much, Victor. Quite technical, but I think it's been broken down for understanding. The last time I heard about the word polymerization was when I was near high school. And I remember the chemistry teacher saying it's a process where relatively smaller molecules called monomers combine chemically to produce very large chains or network called polymers. And so I'm glad to have heard about it again. In the course of the presentation, there were a few thoughts, and I'll kindly call on Dr. Mai to give some clarity to a few areas, after which we shall have questions and answers sessions. So please prepare your questions, and Victor will help answer all those.
Good morning, everyone. I couldn't help but offer to provide these comments, mainly because you did invoke ACI, and I do appreciate that. However, I just want to make sure I set things straight. If you could do me a favor and go back to that slide where it has ACI, the ACI documents. I want to just make sure I put things in perspective. Well, first and foremost, by way of background, I'm a civil and structural engineer. I have my PhD in structural engineering, and I've been working in the area of specialty construction chemicals for over 31 years. And I'm extremely familiar with all construction materials related to concrete. I also happen to have been chair of the ACI Committee 222 on corrosion. So I'm extremely familiar with the corrosion of steel and concrete. And one of the key benefits of FRP is the fact that it is corrosion resistant. That is a key benefit of it. Now, that said, there are things that you need to be aware of. If you do remember dealing with regular reinforcing steel and looking at the stress strain curves for steel, it has yield. It has a yield point, and then it strain hardens, right, before it fractures. And that is very, very critical. However, FRP doesn't do that. It just doesn't. It's a very brittle material. It has a high tensile strength, but it's a very, very brittle material. And that's why you have to be extremely careful when you're designing with it. Now, this is the document on, this is the slide on the ACI documents. what I want you to, if you can project it, okay, it talks about ACI 440.1R, 0.5 specifications and so on. Now, these are guides and specifications, they are not codes. These are not codes. They're just guides and specifications. ACI just recently developed a code, and it's the 440.11-22 code. So now we have a building code. We have a code specifically for FRP. And that will be adopted into the International Building Code, IBC 24, with a couple of exceptions. Now, what are those exceptions? Okay, it says that custom plate structural concrete intended reinforced with glass fiber reinforced polymer, reinforcement conforming to ASTM-D 7957 and designed in accordance with ACI code 440.11 shall be permitted where fire resistance ratings are not required and only for structures assigned to seismic design category A. What is seismic design category A? It's the situation where you have minor shaking. You need to be aware of this. This has limitations in terms of the seismic requirements and also fire ratings. I work in, again, I've been working in materials as a materials consultant, and I just want to make sure that you have the right information. FRP has its place. The key area is with respect to corrosion of reinforcing steel. That is the key area. It does provide some benefits, significant benefits in that particular area, situation. One other thing that I wanted to make you aware about, I didn't hear you talk about that. When we are talking about glass fiber or use of any glass fiber reinforcement in concrete, it has to be alkali resistant. If the glass material reinforcement is not alkali resistant, concrete is a highly alkali material. It will essentially erode or eat up the material. So it needs to be alkali resistant. I didn't hear you point that out, but yeah, no, but that is one of the key things that is very, very critical, in terms of the alkali resistance of the material. And my, overall good presentation, I appreciate that and everything. I just want to make sure that I point people in the right direction. The American Concrete Institute, we just formed a center of excellence on non-metallic reinforcement. We call it NEXT. If you go on the website, you'll be able to access, the website, for NEXT. We do have a lot of information on non-metallic reinforcement, and we also have, courses on the use of how to design using, fiber reinforced polymer reinforcement. And you can access those through ACI University. So I just wanted to make sure I pointed some of these things out. One of the key things is it's a very brittle material. Yes, it has a very high tensile strength. That is not the issue that we're concerned about. You've got to be careful. You cannot take full advantage of the tensile strength. So there are strength reduction factors to make sure you don't get to that situation, because unlike steel, it doesn't yield. And you will end up with a brittle fracture if you go way beyond the limitations of it. All right? Okay.
Great. Thank you so much. So, a look on our faces shows we have a few questions we want to ask. And so if there are any questions, you kindly shoot your hand up. To mention your name, tell us which institution you work with and your area of specialization, then the question goes. Then the resource person will answer them. I see your hand up. Yeah.
Good morning. My name is I'm also a structural engineer. I'm interested in the brittleness of the fiber reinforcement. So how do we solve that problem? If we had to use it in tensile for tension reinforcement. What we do.
Yeah, okay. If you don't mind, I'll answer the question here. Excellent question regarding the brilliance of the material. This is where, you need to use the 440.11 code because it's addressed in there, in terms of the strength reduction factors and everything. You cannot capitalize on the full tensile strength of the material. So all of those things are addressed in terms of the safe use of fiber reinforcement. That's not a problem. I just want to make sure that you know the resources to use. You cannot use your regular reinforced, concrete design, procedures and just assume that okay, it has this tensile strength and so on. So you're going to apply your 0.9 feet factor or whatever. No, that's not going to work. Make sure you're using the 440.11 code document. Everything. It just again, it just came out, and we do have the webinars on it. You can access the webinars online, through ACI University.
Thank you very much. Any other question?
My name is Crown. I just want to find out the mention of reducing the sizes, like if you have 12 mm steel, you can use 8 mm of the fiber reinforcement. Is there a technical data sheet that we can use or rely on to be able to know that okay, if I have this, I have to use something like that?
Yes, Dr.
No, I don't know if you can address, but I'll address.
All right.
Yeah, I just will make a small comment as well.
Yeah.
So first of all, I'm grateful. I'm grateful for your comments, and you're 100% sure. And that was actually when I was making the presentation. You see, I think I spent more than 1 hour just like on the brief from that corner, and I was saying that I cannot explain all at once. I mean, we'll take maybe like 1 day even to talk on whether we can use it, maybe even on a regular slab here, there, like, and again, like the key factors. That's why I was saying you have to address the whole. Thank you very much. Like with the education with regards to that new developments, again, bringing that our attention to that fact. I'm not, and again, I'm not saying, and I never said so, that this material is like Saint Graal, like throw away the steel, throw away everything else, use fiberglass. No, I mentioned that in a particular area, in some particular cases, it is possible to use so. So like you can use it and you can benefit from it. With regards to, again, like, and in continuation with your question, we do have the technical data sheet. We will I mean, we can share it together with the presentation later on, and you will be able to get some information from there. But in addition, as I was saying, we never say that it is like that size to that size. We are just saying that these are the parameters that we as the manufacturers, that are the parameters we are having. Then you are using the design codes, looking on the factors, looking on the properties of your, also your structure, your designs, and like you're just applying all together, and then you will see what you are using, what size you are using. I'm not saying that it's like it's and all of the occasions that I'm just saying that from what we see in the most,
There's one person online.
in the most simple structures, in the most like the regular simple story, wherever, where there is no any hazardous situation, just like regular situation. That's what
We have
you might be saying is possible. But I'm not. I'm here. I made this presentation as a manufacturer, as a producer, and as I'm saying to you, I came here to society of engineers, society of people who are designing, who are creating, to use this material later on in their design for their clients. So you are the ones who are taking my parameters 1, 2, 3, 4, including like the fire resistant things and the other things. And it is true that it is much lower from the steel, and it has to be considered. These factors have to be considered. How to consider this factor? This is the question. The answer to this question, design code, as just mentioned, will give you that one. Because again, we are here. If we will start now, I mean, we have to take the big board, and then like so. And again, there are a lot of other research in that so far, because even for the past months, for example, I'm receiving the latest researches from 2020, 2021, 2024, the alkaline resistance, showing the different parameters. And again, all that is the science. It's not something stable. It's not something that it's just here at the moment. We know everything. We are done. We are finding our things. We don't know. It's like the research is a key point. And at the same time, maybe if you will find some of the parameters for some of the design codes or the recommendation, for example, like that guides and recommendations that you will find there, you might be finding the new articles which are a bit changing the understanding of the material, the behavior of the material recently, like 2019 to 2021. So that's why you are also amending yourself to it. I hope you will agree. So that's what my point.
Great. Yeah. Okay. No, thank you for
This man, if you allow him, he will lecture you.
no, thank you so much for your question. But I think the fundamental couple of things I want to address. Number one is when you talk about tensile capacity, right? Okay, the FRP has a high tensile strength, relative to the mild steel reinforcement, and that's where it gets sort of misleading, that based on if you were to do just a simple tensile test, a small bar, FRP bar, will give the same equivalence as a bigger steel bar. So anything regarding the sizes and everything, I would say just totally disregard. Because when you're designing a slab or a beam or whatever, right, you're dealing with bending moments and cross resistance. So you need to go through the design process, and then based on that, you determine the appropriate reinforcement that you need. The other thing that you need to keep in mind also is the fact that, especially for elevated slabs, you've got to worry about your deflections, right? What your deflection is a function of what? The stiffness of the material. The modulus of elasticity comes into play over there. You have a lower modulus of elasticity with these materials, which means that you plug it into the equations, your deflections are going to be higher. But then you do have your limits in terms of your deflections. Invariably, you may end up using more bars, more FRP bars. So my guidance to you is go through, use the code, go through the process. You'll be able to size the reinforcement appropriately. I went, look, I don't need to give you a hard time with it. I just want to make sure that we have set things straight. Again, as you were told earlier, I'm the current president of the American Computer Institute, and my platform message is expediting the acceptance of qualified new technologies for the built environment. So I'm all about expediting this, and I did talk about the fact that ACI has a center of excellence on non-metallic reinforcement. We're working with Saudi Aramco and ExxonMobil and a whole bunch of other people to promote the use of fiber reinforced polymer reinforcement. But then we got to make sure that we're going through the summer processes. Yeah. So again, you're structural engineers, you know the design processes and everything. Just follow the code and size it appropriately. It's not, don't look for a data sheet that's going to tell you you can use this bar to replace this bar or anything. Not whatsoever. Sure.
Thank you very much. Just again, in continuation to that, just a small adjustment that yes, I have at the moment actually, I have a feeling that we stuck at only the tensile. And it is not true. It is not supposed to be like that. Though yes, it has bigger tensile, but the rebar, the reinforcement, it has the other parameters: shear, compression, elasticity, actually a lot of different parameters that also have to be considered. So that's why fully agree what you said. Just wanted to add that do not look only on a tensile, look on whole. Like this material has its properties, not good, not bad. Some of its properties. The figures are the figures. The way how you are applying it will determine where you are able to use it or you are not able to. That's
Great. We have one or two comments from our colleagues joining us virtually, so we'll listen to them.
We have about 40 something online.
Yeah, there are about 50 people online, so we will have to give them some audience as well.
Michael Paulson. Okay, you asked the question?
Yeah, Michael Paulson.
Michael, can you please ask your question?
Is it muted?
Yeah, yes.
Michael, can you unmute and ask your question?
Peter Paulson. It's Peter.
Peter Paulson. Please, can you unmute and ask your question? Okay, Emmanuel Asante, your hand is up. Would you want to ask your question?
It's gone. It's gone. Okay, so let's find out.
Someone has come by some. Please, are there any more questions? One or two of them, then we can
Where are the structure?
move on to the next session.
I'll call your name. Me? You can give the question. Ask your question. Me? Yeah, look. Aeronautics.
Sorry, someone is asking a question, so let's listen to the question.
Okay.
Aeronautic.
Hi, good morning. Please, I wanted to ask whether the fiberglass reinforcement can be detected by a micro wall scanner.
Okay. Any experience? Can it be used? Can you use the scanner to detect the scanner? Yes.
Well, it's non-metallic, so you're not going to be able to, do that. However, you might be able to use things like ground penetration radar if you need to, but a metal detector type thing, I don't think that's required here.
So this raises the question of if you are going to engage doing structural integrity on such facility, what does of it should be thinking about that strategies involved in doing structural integrity where we have FRP as component. Sorry.
Yeah, those are the types of questions that engineers need to fully understand before getting to full adoption of new technologies like this. We all want to promote new technologies, but issues like this need to be thought through. We just don't jump on it. But I was kind of surprised to see that projects are already ongoing on large scale with this material. As my colleague has been saying, we all want to promote new innovations, but as engineers, safety is our #1 priority. So let's be careful that when we get thrown at these new technologies thrown at us, we understand the engineering implications of it. How do we design for it? What I would like to see, is the first in your presentation, the first thing I would like to see is stress makers for FRP versus steel reinforcement. Because if you had shown that, I think that would have clarified for everyone the fundamental difference in design approaches for the two. So that's what I would say. Do you have stress makers or stress makers?
No.
It's always important to start from fundamental principles, because if you don't, you're going to run into problems.
So these are some of the feedback you need, all right, as a manufacturer. But as part of your data sheets improvements, you add that when you test them, you can get a care. Let's see how it behaves. Well, because you remember Dr. Mines said something about your yield region, which is very, very important. So for me, these are things that we should be looking out for. And it helps the structural engineer in terms of design. All right. There's one online. Okay, let's go.
Yeah. Iman Obochi. Hi, Emmanuel. Can you please go ahead with your question? Muted. Should we switch to? Okay.
Yeah, okay. So my question is, but yesterday I had a privilege to do a presentation at the meeting fire conference. I want to know the behavior of the fiber reinforcement in fire. That is one. And the fatigue behavior. The fatigue behavior of the material. That's when it is loaded cycle, reverse cycle.
Okay, so with regards to the fire resistance, it's this question. Actually, I was expecting this question. The fire resistance, I was mentioning that the fire resistance is much lower compared. First of all, when we will start, when we will come to the material, let's mention the material itself. The material, as I was mentioning, consists of the direct, like the glass filament and the resin. The melting point for glass is around 1,100 plus degrees, something around that. But the melting point for resins is around 300. So because of that itself, on the direct fire, it's very, very, very low. When it comes to the structures, like when it's inside of the reinforced concrete parameters, with the latest articles I've read, it shows that unprotected it's all varies. I mean, now we'll come to the discussion a long time, but anyway, it just varies from the concrete cover, from the concrete cover. With the regular cover, the experiments again, I may share the article later on to go through. It can sustain from 30 minutes, unprotected one, from 30 minutes to 60 minutes on a fire. But with the increased, the increased level of cover also matters. Whether it's the standard, whether it's 40 millimeters, whether it's 60 millimeters, it all depends again. Like engineer just like the of this I just said, it's all varies on the class of the structure of the fire, like the level of the fire protection has to be worked with. Where and how this will also determine the thickness of your slab, of your concrete cover that has to be done in order to prevent the destroyment of your slab, but also the destruction of slab. But also additional points, which also again it's all varies. I cannot give you the straight answer. Like with regards to the direct fire, I mentioned the parameters. With regards to the concrete, but when it's reinforced in the concrete, I cannot say because again it's all depending on the factors and it's all depending on the timing wherever. But that's what from 30 minutes from 30 to 60 minutes. That's what the latest articles I'm having. Also, just kindly consider additional fact about also the thermal conductivity of this material. Right? I think it also works. I mean, by all considered all the tests that we've done with it and the way how. So this is with regards to the to a second question. With this one, a question. Fatigue, yes. That one, I think at the moment I won't be able to reply to that one. It's not one of the common questions to discuss, but though we do have, like, I'm having, because engineers all the time when I'm talking to them, they're having the questions. So I'm having the parts of the also articles with this regards. If you're interested, I can forward it to you. You will be able, I'm sure you will be able to answer this question. It's always the pleasure, and I just want to point additional. If you have questions, that is good, because when you're asking questions, you're also developing the material, you're developing the usage of the material and different type of the structures. So me from my side, I may share the so far the literature that I'm having with because even for example, one of the recommendations so far, it was showing the test methods on a different, based on the different, like the fatigue, the shear at the moment. So we also are trying to get more of the researchers on it, on each part of this parameters, which might be giving additional information to the engineers, because that's also leads to better usage of our material. Because engineers will not. I do agree with the gentleman, with Mr. Mark, that we have to know the material that we are using. It's 100%. I fully agree with it. But I want to say also additional, but that at the same time, I recall that we also have to stay open-minded, the experiments and the further understanding of the material, because otherwise we still would be in a stone age and we wouldn't try anything new. So yes, it is about the trial of anything new, but about the smart trial and smart understanding of something which is in front of you and how you are going to use it. That's what I would.
Can you just add the probably to ACI? You know, for steel bars, for me, when I'm looking at the policy control for steel bar, I'm not too much interested in the tensor. I'm interested in the mass, mass meter. All right, for steel bars, and then I'm interested in the ductility value, where we want to know our ultimate, and I want to know our yield. What is the criteria for FRP? No, is there anything like that? Because structural engineers, for quality control purposes, the mass per meter talks about the kind of impurities we have in the steel bar. Okay. For this, what can we talk about that in terms of quality control? Is it only the tensor? Do you have something like that?
You mean what we are testing?
Yes, what I'm saying is for quality control purposes. For manufacturing, the impurity is very, very important. That accounts for its quality control. I'm saying for steel, in my lab will measure the mass per meter length. For instance, there's a standard for it for the various sizes. All right. For FRP, do you have something like that?
Thank you very much. It's also, with regards to the quality, it's actually a very, very, very critical question, especially in a situation where we are at the moment. However, I will particularly, I will a bit stress it with regards to the size of the steel we are having on our open market and the size that we are using, which also has to be, and that's where we're also suffering, because sometimes when people are coming to us, like not even as people are coming, when somebody is hearing maybe about the 8 mm, they are not thinking that is the correct 8 mm how it is supposed to be, like the 8 mm of the size. They are really thinking about the current at the market we can find around 5 mm. They are selling as 8 mm, which is totally a disaster if this is. The same thing when somebody is selling 12 mm, it is rather 10.5 around that. With regards to the quality control of our reinforcement, how it comes, what do we do, how do we test, and all this. First of all, unfortunately, at the moment, one of these guides are showing the full test. I think there are around 15 or 20 tests that might be performed on GFRP so far. Something like that. Around, it's quite a big list. Though not all of them are critical. The critical are, I think, like 5 or something. They were determined by the technical committee when they were reviewing on the materials. So we do test. We have every batch. Usually the batch is mainly around like 1 month approximately for the raw material which is coming. We have the test reports for the raw material which is coming, which was tested, plus our material. We are using the GSA lab. We are testing the tensile, shear, like these parameters that we are testing at the laboratories. Plus, apart from it, we also insisted that every batch, if client wants to, we are testing the particular batch that we are delivering to client. For example, if this is the project A, and we are delivering some, they are just taking the samples, because the testing for this material is also a bit, okay, it's additional 1 hour of talks. The testing of this material is a bit different, especially when it comes to tensile strength, because it has to deal with the anchors on 2 sides of the bar, because it's a bit different with regards to how to prepare the specimen for testing.
What's the assessment that I use?
ASTM. Like the one I can tell you.
Okay, no, that's fine. I just
Just the regular. It's actually particular for the particular. Just what down. So they are just like, yeah. So yeah, with regards to the testing, maybe the clients may just cut this one to prepare the anchors for them. They don't bring it to any lab, wherever it is. We actually making sure that mainly all of the labs, because we've been just doing the rounds for labs to get to know how to test our materials. So yeah, we like, so any materials, any lab at the client's choice to product might be tested. We have no problem with that, and it's, I mean, we are for it, because clients should make sure that what we bind, the parameters are there and like the quality is there.
No, yeah, I think we spent quite a bit of time on this. I just want to say that despite the nice discussions and everything that we've had, FRP there's a place for FRP. You know, when you leave this place, just keep in mind that there is a code for FRP and there are design procedures for FRP. Please follow the code. You know, follow the code and use it appropriately.
That's exactly what I was also.
Great. All right. Great. Thank you. And for the sake of time, we'll bring the Q&A session to a close. But we will encourage our colleagues online to send as many comments as they have into the chat box. We'll try and collate them and ask the resource questions to